Good morning, everyone. I'm Helen, and I will be talking to you about my project about water quality testing in Lebanon. So I've been working on this project in the mechanical engineering and biomedical engineering department with Dr. Zaman, and we've been working with a professor at the American University of Beirut who is in the Department of Environmental Engineering, and he is, for the sake of this project, kind of our client. So if you hear me refer to client, that would be this professor. So the problem that we need to solve. Little is known about Lebanese water quality. There have been a few studies done. In 2010, USAID did a study. The challenge is that these previous tests had uncontrolled variables, and so what is known about water quality is really anecdotal. Residents only drink bottled water because there is such a concern about the toxicity of the water. So the benefits of knowing what would be in the water is that they can better treat the water and cleaner water sources can be determined. And if you look at this picture here, this is along the side of the Mediterranean Ocean. These are men fishing, and that drain that's coming out right next to the man sitting there is a sewer drain that's going straight into the ocean. So clearly there is an issue of a lack of water management. So our needs statement for the device is that we need to develop a portable, low-cost technology to quantitatively detect heavy metals. And this would differentiate from existing technologies that may only qualitatively detect, are they there or are they not there? This would tell you how much is there. And then the other goal is for this to be used in field research. So kind of the big problem is the metals. We're looking for heavy metals, specifically lead and cadmium, and these come from two different sources. So one source is industrial waste. I mentioned before the lack of water management, so they don't really have a way to dispose of industrial waste. And the other source is from the Lebanese Civil War. The ammunition and bombs that were used in this war ended up deteriorating and going into the water supply. So what's the big deal about having metal in the water? It's in such small quantities that you probably don't even notice it in taste, but there is a huge list of problems that can arise from having metal contamination in the water. The one that you probably are most familiar with hearing is brain development issues in children. You may know this from Flint, Michigan's water crisis, but obviously there are a number of other symptoms. And then these pictures are just two other water sources, again, right on the Mediterranean Ocean. And then the second picture is one I took in a Syrian refugee camp of the well that they are getting their water from. So from that, what is the impact of the refugee crisis on this water quality problem? There have been 1 million Syrian refugees that have come into Lebanon in the past decade. So this equates to a 20% increase in the population. And the local municipalities can't deal with this influx. They don't have the management structure to deal with the waste or the water. So aid organizations have been trying to fill this gap, but it's usually not very effective because they just kind of tax the municipalities more with what they build. There's not really a connection between the construction of waste management for the camps and waste management in the cities. So it will often go just into a river or into a ditch where the refugees are getting their water from. So I'm going to shift focus a little bit onto the device now that we have the background. So what we're doing is we are building a device around calorimetric reactions. So I know there are a few biochemists in the room that may be familiar with what these are, but this is basically when you mix the reactants and you get a color change. So you can see in the pictures there are some color changes. But what we're expecting to see in the Lebanese water supply is more of that purple color change you see on the bottom, which is not nearly as drastic as the top change, which is why a qualitative analysis wouldn't really do what we need to do. These changes are often very subtle, and if you're just looking at them, that's very subject to human error. So what we're trying to do is measure the absorbance of light. So we're looking at the absorbance here, and we're looking for a peak at a consistent wavelength of light. So around 550 is what we've found for cadmium. So we've looked at that peak. And here is just sort of the trend of the different concentrations that are expected in the water supply. So based on the previous study in 2010, we have kind of an idea of the range of concentration that we're looking at. So you can see there's a decreasing trend as the concentration increases, and these all have a wavelength of 545 to 550 nanometers. So moving on from the chemistry to the device, we had a few requirements that our client gave us, is that he wants it to be fairly simple to use, so it doesn't need to be someone who has as much training in engineering and chemistry as maybe we have or he has. The speed isn't critical. We're not looking for something to happen in like 2 minutes, but obviously you don't want to be standing in the field all day, so we want it to be relatively quick to finish. And then 2 requirements that we came up with for ourselves is that we need to filter the debris in the sample. We don't want, for example, sand in the water, because that would be damaging to the equipment. And the maximum size that we can have is that of carry-on luggage. If we were to bring this over to Lebanon, you can see why that would be a good idea. You don't really want to put this in checked baggage or anything like that. And then the inspiration for our design came from PharmaCheck, which I know some of the students in the room might be familiar with from our sophomore class. But what PharmaCheck is, it's a device that detects counterfeit and substandard drugs, and it uses an imaging process and looks at fluorescent reactions. So we're trying to do a similar thing with looking at the absorbance and using the same imaging system. So here are images of the pieces that we have developed this semester. So there are a couple different brackets that you see. The gray images, those were created in SolidWorks, which is a 3D modeling software. And then we were able to 3D print those 2 brackets to hold the syringe, which will dispense the correct amount of chemicals for each reaction, and then the motors, which are controlling the syringes. And then you can also see in the picture the motors that we're using, which are pretty standard motors, and we have this lead screw coming out, which will push the syringe in to measure the amount of chemicals. And then there's also an image of the reaction chamber, which we were able to create on a CNC mill. And you see little holes in there that will be where the syringes come into the chamber to measure out the chemicals, and then it will be imaged through the 2 sides. So here's a little overview of that whole system. So you can see there's a controller, and then the motor and the syringe, which I mentioned, that go into the chamber. And there will be 4 of these. I just was able to get a picture of one of them, but there are 4 syringes, 4 motors, and obviously the 1 chamber. So how our device compares to other devices, you can see across the top that there are kind of 3 different price points here. So our device is this $1,200, and then the other 2, $5,000. This Horiba is the accepted kind of field method of testing, and spectrophotometry is the lab method, so what we've been using to calibrate. And these test strips that are $20, you may say, well, why don't you just use the $20? These are the qualitative, this is a qualitative test, so I don't know. Some of you may know a pH strip that you stick into water, it changes color, you look at the chart, say, oh, it's blue, and you have a range. So that's not really effective when we're looking for such small concentrations, which is like maybe less than 1/10 of a milligram per liter. And then the other things on here I just have whether they're qualitative or quantitative. So ours is quantitative and can be used in the field, which were the 2 goals that we were aiming for. And it's much lower cost than $5,000. So what are the large-scale implications of this? In the immediate, we are extending the partnership that our lab has in Zanzibar. This summer, some students are going to be going and working on water quality there, because they also have the issue of not really knowing what's in the water, not having done a lot of testing, and not having a lot of water management. And then in the longer term, we hope to be able to adapt this device to test for many metals, because there are contamination issues in a lot of countries. If you can see on this map, the darker the country is, the worse the problem is. But it also is important to remember that even if the country is white on this map, water quality is still really an issue, as we know from Flint, Michigan. So even though the US is white on the map, there are still problems with contamination from heavy metals. So I would like to conclude by saying thank you to everyone who's worked on this project with me this semester. The 5 students are pictured on the bottom who've been working with us, and then I also want to say a big thank you to Dr. Zaman and everyone in the lab and our engineering advisor, Dr. Hauser. Yes.
So is the goal of this to tell people what water they can drink and what water they shouldn't drink?
The goal of this is a bit more back on the research chain. The professor that we're working with in Lebanon wants to kind of do the tests that haven't been done so they can understand water quality sources and what's best, what is a real problem, and then try to figure out how to implement a water management system. Yeah.
Were you interested in lead and cadmium just because those are really hard to detect and that there are other ways to detect maybe other pollutants?
Yes, so heavy metals are harder to detect than biological contaminants, but why we're interested in those is because they are the 2 most common in the water sources in Lebanon, and they are also 2 of the most dangerous. Anyone else? Okay. Thank you.